Welcome guys to a video on IIT JAM 2020 differential equations. So we have tried to give solutions for all the problems from this area, that is differential equations, for this IIT JAM 2020 examinations. So we start with the first problem. So if u is x cube and v is y square, then transform the differential equation 3x power 5 dx minus y times y square minus x cube dy equal to 0 to dv by du is equal to alpha u by 2 times u minus v. Then alpha is 4, 2, minus 2 or minus 4. So in this problem, what we can do here is we can just rewrite the differential equation to something of this kind, that is x cube times 3x square dx minus y square minus x cube 2y by y dy is equal to 0. So once we do this thing, what we have is, like, when you substitute u as x cube and v as y square, then du is actually 3x square dx and dv is 2y dy, and all these things going to this particular differential equation will give you something like, if you substitute, you will get something like u du minus v minus u by 2 dv is equal to 0. So if you just rearrange it, and then what we are going to get is something like dv by du is equal to minus 4 times u by 2 times u minus v. So if you compare with this part given in the question, we will get that alpha value is nothing but minus 4. So it's comparatively a simple question. So now we go to the next question. If x square plus xy square is equal to c, where c is a real number, is a general solution of the exact differential equation m dx plus 2x by dy equal to 0, then we have determined the value of m of 1, 1. So here we say a differential equation of the form m dx plus n dy equal to 0 is exact if there exists some function of x and y, say it is u, that is u of xy equal to c. If there is some function like this for which the total differential of that particular function, that is total differential of u, should be equal to the LHS part of this differential equation, that is m dx plus n dy. So if you have a differential equation of this form, if you want it to be exact, there should be some u for which du should be equal to m dx plus n dy. But du we can rewrite as, we know it is dou u by dou x dx plus dou u by dou y dy. So what we get is dou u by dou x is nothing but m, and dou u by dou y is nothing but n. So here we have something like n, that is dou u by dou y is nothing but 2xy. From the differential equation we have that. So if you integrate it with respect to y, you are going to get something like xy square plus phi of x. If you are going to find out, or if you are going to differentiate this u, what we got here with respect to x, we get dou u by dou x, which is nothing but our m. So what we get is, if we differentiate with respect to x, we get y square plus phi dash of x. And the solution we know is basically given by, for an exact differential equation, it is given by integral over m dx, where y is kept as constant, plus terms in n, that is the second term, terms in n not containing s, dy equal to c. So that will give the solution actually. So if you choose this m what we got, and if you are going to find the solution over here, because the second term, that is terms in n not containing x, there are no such terms here. There is only one term which contains x. So what we get is integral y square plus phi dash of x dx is equal to nothing but xy square plus phi x. And if you compare this general solution is given to us, that is x square plus xy square equal to c, we can say that phi of x is nothing but x square. Thus we get that m is nothing but equal to y square plus phi dash of x, that is phi of x is x square, so phi dash of x is 2x, so we get m is equal to y square plus 2x, and at m 1 1 we get the value as 1 square plus 2 times 1, that is equal to 3. So here you can see, if you have a doubt, you can see why we took this phi of x here is because here we have like dou u by dou y is 2xy for a function of x and y. When you differentiate partially with respect to y, we get 2xy. So that means that like if you take this particular u what we have written over here, and if you differentiate with respect to y, you're going to get what? Same 2xy. That means we could have something like a phi of x also there for u. It is possible that the function u could be actually something of this kind also, because when you differentiate with respect to y, you keep the terms in x as constant. So you have to assume this like this. So the solution for this problem is actually 3. So the next question is that f from r to r be a differential function with f dash x is equal to f of x for all x. And suppose that f of alpha x and f of beta x are two non-zero solutions of the differential equation 4 d square by dx square minus p dy by dx plus 3y equal to 0, satisfying f of alpha x times f of beta x equal to f of 2x and f of alpha x times f of minus beta x is equal to f of x. Then we need to find the value of p. So first of all, we are going to find what is the function f which can be used here. So we are given f dash x is equal to f of x, or d by dx of f of x minus f of x equal to 0, or we get df by f is equal to dx, or f is equal to c e power x. You can see if you take this kind of a function and if you differentiate once, you get the same function again. You differentiate c e power x, you get again c e power x itself. So now then we can say that f of alpha x is e power alpha x and f of beta x is c e power beta x. So if you see the first condition given to us, that is f of alpha x times f of beta x will be equal to f of 2x for these two non-zero solutions. What we get is c e power alpha x times c e power beta x is c e power 2x. This is actually c e power 2x, or from which we get c square e power alpha plus beta times x is equal to c e power 2x. Now if alpha plus beta is not equal to 2, then what we can say is that these two functions, that is e power alpha plus beta x and e power 2x, these two are actually linearly independent. Then if you just take this to the left hand side, what you get is c square e power alpha plus beta x minus c e power 2x equal to 0, and since they are linearly independent, we can say that c equal to 0. But if c equal to 0, f is 0, but we need f of alpha x and f of beta x to be two non-zero solutions, so c cannot be 0, right? So what we must have is that alpha plus beta has to be 2. So if alpha plus beta is 2, then we get from the same equation, substitute here as 2, we get c square minus c times, and you take this to the left hand side, you get c square minus c times e power 2x is 0, and e power 2x is not 0, or is never 0, so c square minus c has to be 0, and we get c into c minus 1 has to be 0, or c is 0 or 1. And in fact, or obviously we have to take c as 1, otherwise we cannot get such f. So f of x has to be e power x. Now similarly, the other condition, second condition, will tell us that alpha minus beta has to be 1 also. So we get two equations here, alpha plus beta is 2 and alpha minus beta is 1, and thus if you solve these two, we get alpha and beta to be 3 by 2 and 1 by 2. Now we got f of alpha x as e power 3 by 2x and f of beta x to be e power half x. Actually, when you have a differential equation of this kind, that is a differential equation, second order linear differential equation with constant coefficients, we can have three types of solutions. That is, if when you write down the auxiliary equation for this particular differential equation, you get a second order you get a quadratic equation, which if you solve, you get two roots. It could be real and distinct roots, it could be real and equal roots, and it could be complex roots. And depending upon these three type of cases, we have different solutions listed out. So here we need to get, and we know that if there are real and distinct roots, the solution is given by c1 e power m1x plus c2 e power m2x, where m1 and m2 are the two roots of the auxiliary equation if they are real and distinct. So here we already got like two solutions, like e power 3 by 2x and e power 1 by 2x. So what we have is nothing but these two has to be the roots of the auxiliary equation, or we get the auxiliary equation as something like x minus 3 by 2 times x minus half, or simply m minus 3 by 2 times m minus half equal to 0. And if you just simplify it, you get 4m square minus 8m plus 3 equal to 0. So that means this is nothing but the auxiliary equation for this differential equation, satisfying like for some f satisfying all these conditions. So what we get is that p has to take the value 8 to get this for the such an f to exist. So the answer is actually p is equal to 8. Now if we move on to the next question, it is we are given a differential equation y minus y square dx plus x dy equal to 0, and we are told that if 1 by x square plus y square is an integrating factor of L of y equal to 0, then which of the following are true? So we are given kind of exact differential equation here, problem in that area, because differential equations which are not exact and are of the form m dx plus n dy equal to 0 can be made exact by multiplying by suitable integrating factors. And so here if you see in this problem, we are given that 1 plus x square by 1 by x square y square is an integrating factor. So if you multiply that with the given differential equation, what you're going to get is something like this: 1 minus y by x square by dx plus 1 by x by square dy equal to 0. So if you see, then m is actually 1 minus y by x square y, m is actually 1 minus y by x square y, and n is equal to 1 by x y square. And if you find dou m by dou y and dou n by dou x, you have exactly minus 1 by x square y square. So we have that the differential equation is exact. Now the solution is given by integral over m dx, where y is constant, plus terms in n not containing x dy equal to k. There is an n here missing, sorry for that. So if you substitute your m and these things here, what we get is integral 1 minus y by x square by dx, plus there is no terms of this kind, because in n, that is x, there's only one term and that is containing x, so there is no term here. So we simply get this integral is equal to k, and when you integrate it, we get something like minus 1 by xy plus 1 by x equal to k, or thus just rearranging it, we'll get y equal to 1 plus kxy. So what we get here is solution is y equal to 1 plus kxy. And you should also notice that k could be negative, so 1 minus kxy is also a solution. Here we have taken k, the constant as arbitrary constant as k, it could be minus k also. So yeah, so what we get here is if you look into the options, y equal to 1 minus kxy is a solution, but here it is given that y equal to 1 minus kxy is not a solution, so this option is not true. Here we have minus 1 plus kxy, but that is not correct. We have 1 plus kxy, so B is false. Here we are given y equal to minus 1 plus kxy is not a general solution. So that is actually a correct statement, because we are getting y equal to 1 plus kxy is a general solution. And the last one says that y equal to 1 plus kxy is a general solution, but f is not an integrating factor. But here f is actually an integrating factor. So the option C is correct. So the next question is, we are given a differential equation, an Euler Cauchy differential equation here, and that is x square d square y by dx square plus px dy by dx plus qy, and where p and q are real constants. And also we are given that let y1x and y2x be solutions of L of y equal to 0 that satisfy few conditions. That is y1 of x naught is 1 and y dash of x naught is 0, y2 of x naught is 0 and y2 dash of x naught is 1 for some x naught greater than 0. Then we are given 4 options and we are asked to check which one of the following is correct. So here, to discuss the first 2 problems, we are going to go by the method of wronskian. But before that, we'll see how we can convert this second order differential equation, that second order Euler-Cauchy differential equation, into an second order linear differential equation. For that, we just use the substitution as x equal to e power t, and we get y dash is equal to e power minus t dy by dt, and y double dash we get as e power minus 2t times d square by dt square minus dy by dt. And if you substitute all these things in the differential equation, we get the differential equation as d square y by dt square plus p minus 1 dy by dt plus qy is equal to 0. So if you go with the wronskian property, as I told in the beginning, like if you find the wronskian for these 2 solutions at the point x0, you get the value to be 1. The determinant of this 1 into 1 minus 0 into 0 is 1. So we can say that when the wronskian is a non-zero value here, we can say that these 2 solutions are linearly independent throughout in the interval 0 to infinity, and hence we can say that y1 is not a constant multiple of y2. That is just not a multiple of, like, y1 is not something like some k times y2. So what we can conclude is that A is true and B is not. Now for the next 2 options, like in option C, if you are going to give P equal to 1 and Q equal to 0, the differential equation becomes basically d square y by dt square equal to 0, and thus the auxiliary equation is m square equal to 0, and you get 2 roots as zeros. So we have real and repeating roots. So solution is given by c1 plus c2t e power 0t, or simply c1 plus c2t. And if you take back our substitution, that is x is equal to e power t we are given initially, then what we get is the solution to be c1 plus c2 ln x. So if we choose c1 to be 0 and c2 to be 1, we will basically get ln x as a solution, and if we choose c1 to be 1 and c2 to be 0, we get 1 as a solution. Thus option C is actually a true statement. Now to verify whether option D is true or not, we'll just substitute x, the solution y equal to x, in the differential equation, original Euler-Cauchy differential equation, and what we get is x square times 0 plus, because you can see here y is x, so dy by dx is 1, so d square y by dx square will be 0, so x square times 0 plus px into dy by dx is 1, because x is 1, we have y to be x. So we get this, which is nothing but equal to p plus q times x, and we already have given the 4th option, that, or option D, that p plus q is not equal to 0, and x is already greater than 0, so this quantity is never equal to 0. That means x is not satisfying this Euler-Cauchy differential equation. That means that x is not a solution of this particular differential equation. So what we get is that option D is false. So the only correct option here is option there are two correct options here, option A and option C. So the next question is, we're given again an Euler-Cauchy differential equation, and we need to find a solution of this Euler-Cauchy differential equation that passes through the point 1, 1. So similarly, like in the previous problem, we are going to convert this into a linear differential equation, second order linear differential equation with constant coefficients, by using the same substitution x equal to e power t. Before that, first we are going to divide it by 2 completely here, and then we are going to give the substitution x equal to e power t, and we can reduce the differential equation to something of this kind. That is d square y by dt square plus 3 by 2 minus 1 dy by dt minus y by 2 equal to 0. Or then we have the auxiliary equation to be m square plus m by 2 minus half equal to 0, and the roots we are going to get as half and minus 1. So since we have real and distinct roots, we have solution to be c1 e power m1x, that is m1 is here half, plus c2 e power m2x, that is m2 is actually minus 1. So we get solution as c1 e power t by 2 plus c2 e power minus t. And if you take back our substitution we have given initially, you get c1 root of x plus c2 1 by x. So it's clearly you can see from here that if you give C1 as 0 and C2 as 1, we get our solution A. And other three options are not possible from this particular general solution by giving arbitrary values for C1 and C2. You should note that C1 and C2 are not functions of x, they are simply some arbitrary constants. So we cannot obtain obtain B, C and D from this. So the answer is y equal to 1 by x, and you can see it passes through the point 1 1. Now the next question is that if f of xy equal to 0 be a solution of the homogeneous differential equation given here, and if f of x plus alpha y minus 3 equal to 0 solution of the differential equation given, then the value of alpha is what? That is what we have to find. So what we do here is that given that f of x plus alpha y minus 3 equal to 0 solution of the differential equation 2x plus 5y minus 1 dx plus 2 minus x minus 3y dy equal to 0, we replace x by x minus alpha and y by y plus 3. Then what we get is f of x minus alpha plus alpha. We just substitute over here. Y plus 3 minus 3 equal to 0 will be a solution of 2 into x minus alpha plus 5 times y plus 3 minus 1 dx plus 2 minus x minus alpha minus 3 times y plus 3 dy equal to 0. So rewriting, you get f of xy is a solution of 2x plus 5y minus 1 minus 2 alpha plus 14 dx plus x minus 3y plus alpha minus 7 dy equal to 0. So if we just compare this with the initial statement given to us that f of xy equal to 0 is a solution of the homogeneous differential equation 2x plus 5y dx minus x plus 3y dy equal to 0, what you can say is that minus 2 alpha plus 14 has to be 0 and alpha minus 7 has to be 0. That implies that alpha is 7. So the value of alpha is 7 here. So in the next question we have here is actually a differential equation, a first order linear differential equation, and the right hand side we have actually in the differential equation we have actually a function f of x, which is actually a continuous function such that limit x tends to infinity f of x is equal to 1. Then we need to find the value of limit x tends to infinity y of x. So we have that differential equation, first order linear differential equation, we can solve it, and the solution is given by y into integrating factor is equal to integral f of x times integrating factor dx plus c, where integrating factor is nothing but given by e raised to integral 10 dx. Actually whatever is coming as coefficient of y is taken here, so e raised to integral 10x, so 10 dx, that we get as e raised to 10x. So we get the integrating factor as e power 10x. So if you substitute here in this equation, you get y into e power 10x equal to integral f of x e power 10x plus c, and hence you get y is equal to e power minus 10x integral f of x e power 10x plus c e power minus 10x. And we just need to find the limits here. X tends to infinity y, so that is nothing but this statement. And here you can see this limit will become 0 because when x tends to infinity, this 1 by e power 10x will become 1 by infinity, or it will tend to 0. And we just need to care about this part of the limit. So we are also given that limit x tends to infinity f of x is equal to 1, and f of x actually is a continuous function. When you give x tends to infinity, you can see this numerator tends to infinity and the denominator also tends to infinity. So in that case we apply the L'Hopital rule and we differentiate top and bottom, that is the numerator and denominator, and we get something like this, f of x e raised to 10x by 10 e raised to 10x, and this e power 10x will cancel out on numerator and denominator, and we'll have the answer as when you apply the limits you have the answer as 1 by 10, that is 0.1. So the answer to the question is 0.1. So thank you for watching this video. Please subscribe my channel for getting further updates. So thank you.